All right, so this cosmological constant that Einstein used in his, when he originally applied the theory of general relativity to the universe as a whole, to prevent it from being dynamic, to prevent the universe from giving a dynamic solution, as it did when he first applied the equations. He introduced this cosmological constant, and that. He didn't really have a good reason to introduce this, other than the fact that in his mind, he just could not possibly imagine a universe that was different in the past than it is today. And so he as it says here later on, he called it the biggest blunder of his life. Although this cosmological constant has found new life, but in a totally different way. Okay, so now this cosmological constant, some people in cosmology are using the idea as the explanation for the acceleration. Right? It's of course this the cause of the acceleration in the universe that was observed back right around the year 2000 or so, has been given a name. It's called dark energy. That's what's causing it. Again, we don't know what dark energy is, but it's causing the expansion of the universe to accelerate. It's though the universe there's some kind of like spring causing a spring was compressed and is pushing and stretching out the universe, and as time goes on, it's stretching it out even more, much faster, or more accelerated, in other words. So that is what that's this idea of the dark energy. Maybe it has something to do with this cosmological constant that Einstein originally used, but now they're using it in a different, modern cosmologists are using this idea in a different way. It still doesn't give us, the way that they're using it is to try to, mathematically account for this expansion of the universe, or the change in the rate, right? So if the Hubble constant, which is still, by the way, still called a constant, that's the whole idea. The Hubble constant is not constant. That was what was discovered, right? It's not. The expansion rate is 70 kilometers per second each megaparsec, right? So each megaparsec, something is moving 70 kilometers per second faster, okay? But that has been changing slowly over time, and we're getting larger and larger numbers. And then, it doesn't change like instantly. We're looking at billions and billions of years back in the past. More than 10 billion years ago, we're expanding now faster than the expansion rate of the universe is faster. By a slight amount, but it's a slight amount enough to be measured, and for the entire universe to do this, it requires an incredible amount of energy, and that's why it's called dark energy, because we don't know what it is. But it's kind of reminiscent of dark matter, which, of course, remember, dark matter has to do with the rotation curves of galaxies, and explaining why the stars at the outer edges of galaxies are moving much too fast to be accounted for by all the matter that we can observe, that's giving off electromagnetic radiation. So we've come up with this idea of dark matter, and there's evidence of that, right? There's evidence when you look at the rotation curves of galaxies, even our own galaxy. There's dark matter around it. So this dark energy seems to be the cause of whatever it is. Which, again, this is a big mystery, part of 21st century astrophysics. One of the central questions: what's the dark matter? What's the dark matter? What's the dark energy? Anyhow, so this is when we work out the dark energy, and we apply this idea to cosmology, we actually get so what this is showing is it's including the acceleration that we now know about. With that, we can actually estimate the age of the universe. Remember how we did it? We did it before, or you're actually going to do some examples in homework if you haven't done that already, where you just take the inverse of the Hubble constant, and you get about the value of 70 kilometers per second per megaparsec. You take the inverse of that, you get an answer of roughly 14 billion years. So adjusting for the dark energy, we get a value closer to about 13.7 or 13.8 billion years is the age of the universe. All right, so with that in mind, let's look at what we know. Let's see. Of course, remember the globular clusters are ancient, right? The globular clusters that we see around the Milky Way galaxy and around other galaxies are really, really old stars. So the universe began roughly 14 billion years ago. That with an event called the Big Bang, which happened everywhere at once. Where everywhere was a single point of infinite density. There was no outside, right? That's a strange thing to imagine, but that's what we think about when we think about the Big Bang. So the Big Bang occurs. Out of that pours, all the matter, all the energy, all space, and all of time that's ever going to exist. Roughly about 1 billion years or so after the Big Bang, and we're actually going to talk a little in the next chapter about what takes place, for how do we get to the point where atoms are created, and basic things, even more basic than atoms, how do electrons come into existence, how do protons come into existence. But anyhow, about 1 billion years or so, we estimate after the Big Bang, there is the first quasars. Remember, these are these quasi-stellar objects, which are really just AGNs, right, active galactic nuclei, but they're very, very distant, and they're pouring out tremendous amounts of energy. And remember, these are like these, supermassive black holes, which are, feeding on the accretion disk around them. And there's tremendous amounts of material that's falling into the accretion disk. All right, so roughly 10 billion years ago, we get the first stars that are forming in our galaxy. So that, of course, started with the quasars, right? Those are the oldest stars. All right, so what evidence do we have? Really, until the 1964, there was really still available what was called the steady state theory. So there were these two competing theories, starting in the I think I mentioned this before, in the late 50s and into the early 60s. In the early 1960s, there was this theory called the steady state theory, which was you could have originally, when you go back to the time of Einstein, which was a good generation before, everybody would have been considered a steady state theorist. That is, the universe essentially has never changed, right? And so those ideas lingered for a long time, and then of course slowly people started coming up with this idea of of the Big Bang, right? Of a universe that had a creation, a moment of creation. And the thing is, when people thought about this, they realized that wait a second, if there was this Big Bang, there must be some remnant, some electromagnetic remnant of that event, or some event that is close to the time of the Big Bang. And in 1964, there were these two guys right here. This is Penzias and Wilson, who won a Nobel Prize for this. They see this antenna behind them. It's in New Jersey. It's still there. It's actually a national monument now. And they were working for a little company called AT&T, and they were using this thing. It rotated. You see where this wheel is? It rotated that way, and then it rotated so you could rotate it basically in any direction. And this was called the feed horn antenna. And so microwaves came in to this thing, and then they could detect it. It was actually originally used to just communicate with satellites, right? That was the idea. But Penzias and Wilson actually noticed that there was this kind of annoying little hiss, and it wasn't really a sound. It was electromagnetic noise, if you will, and this hiss was coming from every direction, and no matter whether it was day or night, since they were near New York City, they pointed the antenna away from New York City. They thought maybe they were getting some bizarre radio station or something like that from New York City, but it wasn't. It was always there. It was always at the exact same frequency, or you could also say it was always at the same wavelength, and they were just baffled. They weren't even looking for this, right? They were not looking for the evidence of the Big Bang, but that's what they found. They actually found the echo, if you will, of the Big Bang itself, and that's what the cosmic microwave background is. It started out at a incredibly high, a much higher, a much smaller wavelength. In fact, in the gamma region, right after the Big Bang occurred, the photons were in the gamma region, and of course, because the universe has been expanding ever since, those photons have gotten stretched, and they've been stretched out to, and now they are around 1 millimeter in wave. The wavelength that it peaks at is right at 1 millimeter. Let me see. Did they show that? Yeah. So right now it peaks right at about 1 millimeter. Well, this is showing the frequency, but if this was wavelength down here, this would be right at 1 millimeter. So back during the time of the Big Bang, it was right around. It was in the gamma region, and then over time it reduced as the universe expands. This thing, there's a redshift essentially. That's exactly what we're seeing. But we're seeing the redshift from the universe itself. That's this cosmic microwave background. So these are the like photons that. It turns out that the photons that we're actually seeing from the cosmic background radiation, they're about 400,000. They were created about 400,000 years after the Big Bang it occurred. The temperature of this background radiation is about close to 3 Kelvin. It's actually closer to about 2.7 Kelvin. And in fact, there you go. So there's where the peak is. And again, this is something that won them a Nobel Prize. Later on, many years later, we sent up several satellites. One was called COBE. That was in the 1990s to look at to explore the cosmic background radiation, and then more recently there was one called WMAP that did an incredible job of looking at the background radiation in extremely good, fine detail. And that's really the beginning of what we're going to talk about in chapter 27, is what WMAP found, or the kind of details that WMAP found. All right, so that's it for chapter 26. The cosmology, the study of that's it for that chapter. It continues on into chapter 27, which of course is the last chapter of the semester. All right, very good.